Okay, let's start the session. It's nice to see all of you here attending this conference. My name is Dmitry Yamanov, and I'm one of the Firebird co-developers. And my today's session is dedicated to a common review of the Firebird development in this year and what is going to happen in the next year. We will cover the recent releases, point releases, what maintenance releases are expected in the next year, and also most of the time of this session will be dedicated to the development process of Firebird 3 version, what were the plans, what is already achieved, and what is still remaining in the pipeline, and what release schedule should you expect for Firebird 3. What has been released by the project this year? There were two Firebird releases, Firebird 2.1.4 released in March, and Firebird 2.5.1, as you know, was our latest point release. It has been released very recently in October. As you can see, both releases contain a lot of bug fixes, and if you followed the project release schedule, you could know that both these releases were quite overdue in time, because we were trying to collect all the issues that were reported. It's especially true for Firebird 2.5, because, you know, every major release has some issues that are never noticed during the beta testing or release candidate testing, and only after setting up this new version for production, people start to notice any problems. Well, with life, we cannot do anything with that, but as a result, we have quite a lot of issues being reported after the final release. So this is why we didn't really attempted to make any fast release, because the bugs were still reported, mostly quite minor bugs, but anyway. So it could end up with maybe every couple of months we should be releasing new patches. It doesn't make much sense, and it really costs the project a lot of resources. So we were waiting until the snapshot builds were proven by the customers that as good enough in quality. And after that, the first point release appeared. Mostly it contains bug fixes, but also a few improvements, especially in the performance area, and I will talk about that. Now, what new features and improvements Firebird 2.5.1 has introduced? Of course, every point release, it's mostly a maintenance release. It's targeted bug fixing, but nobody actually prevents us from introducing some improvements as well, especially if they are quite easy to implement, so they cannot affect the stability, but at the same time they are useful to our customers. So first of all, Firebird 2.5 has introduced SQL states accordingly to the SQL language specification, but it was available only on the client side. Now this error code is also available in stored procedures, triggers, and so on as a context variable, similar to GDS code and SQL code. It's quite a minor improvement, but it really brings Firebird features in sync with each other, because actually we have some differences in this regard. So this error code was not available for handling in the piece procedure SQL language. Other enhancements. When the optimizer tries to make the cost calculations, it's using a few statistical variables, a few statistical numbers. One of them is the table size, but the table size, it's quite hard to know exactly, because of course the optimizer doesn't count all rows. It's just too expensive. So it just makes quite rough guess by counting only data pages and trying to understand how many records can fit single data page. Because every record has the format of the fixed size, and this estimation can be done quite easily. But nobody knows what is the actual compression ratio for the records. They can be compressed quite good enough, but some records may be not that well compressed. So far, the optimizer was using a constant value. It just imagines that every record stored on disk is actually twice as less as the one stored in memory. So the compression ratio was always considered being equal to 2. Now, starting with Firebird 2.5.1 and also 2, it's going to appear in the next point releases of older Firebird versions. There was some improvement that the engine scans a few data pages and calculates the actual compression ratio on those pages, and then estimates the whole compression ratio based on these tries. Of course, it's still not really exact, but it's anyway much better than a hard-coded constant. And of course, the testing on the field, the testing in production systems showed that sometimes this change really makes the plans generated by the optimizer much better than before. A number of changes were done in regard to the global temporary tables. Maybe the most important of them, at least for some of our users as reported by them, was that the global temporary tables are now allowed to be written in read-only transactions. Because, of course, temporary tables are stored outside the database, so they don't affect the stored data. And why not allowing them in read-only transactions? And what it provides for you, our users. It just allows quite hard, sometimes, calculations using temporary tables for storing temporary resulting sets. But at the same time, it can be done with read-only transactions that doesn't affect the garbage collection. So those of you who actually used read-only transactions for only selecting data, maybe it could be long-running transactions for the whole application. Maybe it could be short-lived transactions. But anyway, you can now populate temporary tables, select from them, and implement whatever complex logic using temporary tables in read-only transactions. Also, there were a number of performance improvements regarding temporary tables. Maybe Vlad will be talking about that in his session. They are related to garbage collection and other areas to be discussed in detail a bit later. They were also quite simple, but it turned out to be to provide interesting results, a change in the GBAC restore performance. The algorithm used by GBAC when inserting records into the database while restoring the database has been optimized, and As a result, it allowed quite noticeable performance improvements, but quite noticed, well, the tests showed something from 20 to 40% of improvement, quite big enough. But this improvement will be really noticeable only on a CPU-bound restore. Of course, if your restore is mostly getting maximum on your hard drive and almost never raise the CPU usage, it's unlikely to show any big improvement. And also, if you perform a restore via the network, of course, network round trips also affect the overall performance. But if you restore the database using the services API, so it's done on the server, and no network round trips are involved. And also, if your database can fit your file system cache quite well, so the most operations could be done in memory, you know that the restore process is performed with the forced write turned off. So most load is dedicated to the file system cache, and only then the data flushed to disk. So this really allows to see you some improvements in this area. Of course, nobody can guarantee what would be the improvement in your particular case, so please test and report back. Also, one more feature is an ability to cancel waiting inside the log manager. It's about disconnecting your users from the temporary tables, from the monitoring tables, or performing a database shutdown. You expect it to execute immediately. But if some request is waiting inside the log manager for the resource to become available, it's not going to react immediately, unfortunately. This improvement makes it possible and allows really a fast shutdown and disconnection. And those of you who were claiming that statement identifiers in the monitoring tables is not persistent, it can change from when you select from the monitoring table different times. Finally, this issue has been addressed, and these IDs are now persistent, the same way as transaction IDs and attachment IDs. But they are still only in memory, so they are not stored anywhere in the database. They don't have to be reset. It's just some in-memory counter that is synchronized across all the attachments, including classic and multiple processes. Now, what could happen in the next year? Firebird 2.0 version series. The last point release has been released quite a lot of time ago. We were always declaring the lifetime, the maintenance period of point releases is one release per year. But as you can see now, the following point release of Firebird 2.0 is already 4 months overdue. So it would be the first in the pipeline to be released the next year. It doesn't have a lot of bug fixes, but actually this version series is not maintained as actively as more recent Firebird versions. Only critical bug fixes are coming into Firebird 2.0. If you were following Firebird roadmap, there was a warning that Firebird 2.0 could be deprecated quite soon because it's already 5 years old. But no decision has been made yet. It is possible that Firebird 2.0.7 will be the final point release in this series, but that it's still possible that other point releases could follow. It will be decided by the Firebird team and will be announced separately if any decisions are made in this regard. Of course, after having point releases this year, it's quite expected that the next point releases will appear the next year. Yes, we are hoping to deliver them in time, but you can see number of bug fixes. For example, Firebird 2.1.5 has enough bug fixes, but still quite less than usually when we release a new version. Firebird 2.5.1 has been released, but the next point release, 2.5.2, are still not buggy enough to be updated. So we will be just following the reports in the bug tracker and reacting when necessary. Also, as our primary focus is now Firebird 3, and we really expect the early alpha release quite soon, it could compete with these two last point releases. So actually, what quarter they're likely to be released depends on Firebird 3 Alpha 1. If it will be ready, for example, in March or in February, our efforts will be dedicated to Firebird 3 Alpha. Only then, these point releases will be attempted to create and release in public. Now, the most important part of this presentation is dedicated to Firebird 3, and let's start with a short summary. Actually, it's more than 2 years of development already. It started quite a long time ago, and it was some initial implementations and initial cleanups were done alongside with Firebird 2.5 being developed, finalized for release. We have more than 400 tickets assigned for Firebird 3. It includes both bugs, some minor improvements, major improvements, features in all the areas in the SQL language and so on, in the performance area. And as you can see, most of them is already addressed. And these numbers show that we are getting really closer to seeing the Firebird 3 released as alpha for the public testing. If you follow Firebird 3 a little bit, you could notice that Firebird project has the snapshot builds of Firebird 3 available for a long time already, so you could already try to download and play with that. So actually, it's not about making it available to you. It's about establishing a point when we consider most of the tasks are completed, so we could concentrate on bug fixing, stability, performance optimizations, and making further to the final release, going further to the final release. In Firebird project, alpha release means that the key tasks are done and the ODS is established and tested to be just persistent and not volatile anymore. It doesn't mean all the features are there, just the most of them, the most important ones, so you could start testing. It also means that you don't have to back up and restore with every snapshot builds after alpha, because the ODS is stable. This is the goal for the alpha release, and it's really coming close to this point. So you will see it in the new year. More than 2,000 of changes have been committed, and they include actually not only features or bug fixes, but a lot of code optimizations, a lot of code cleanup to remove some outdated code. Starting with Firebird 3, only one ODS version is supported. It's native ODS 12. So Firebird 3 will not work with database with all the ODS versions. You will have to back up and restore. As a result, it allowed us to clean up a lot of conditional code that was actually not only affecting performance in some areas, but mostly it was causing bugs because, of course, when we release any new version, it's being tested only in its native ODS. So if you try to use it in production with a database with older ODS versions, nobody guarantees it will work correctly. We do our best to ensure that, but no guarantees are provided. And actually, our bug tracker shows this quite good because sometimes bugs are reported against the problems appeared only with older databases. Now, we have performed a major cleanup to remove all the conditional code. So now, the native ODS is only one, and it allowed us not only remove the outdated code, but it also allowed us to optimize the engine in the best way just for the single ODS. Also, Firebird 3, from the end user point of view, looks a bit different. Let's see. This is the disk layout of the Firebird 3 installation. As you can see, there is no bin directory anymore. All the binaries are in the root directory. And there is only one executable, Firebird executable. It combines both super server and classic server. You just set up the server to the working mode that you need. If you need SharedCache, you set up it for super server. If you need multiple processes with when crash of any of them doesn't affect others, you choose the classic way and just change the configuration to reflect your desires in this regard. So actually the package is the same. You just download Firebird 3 and then set up it to your needs. I will speak about the options to set up all these architectures a bit later. Just a brief introduction of the features. There will be a dedicated session about new language features of Firebird 3 by Vlad after my session. So he will cover all the details, all the examples. This is just a short list. And please pay attention. These are the features already implemented. So you can test it in the snapshot builds right now, and they will be available, of course, in the alpha release as soon as it arrives. So pay your most attention to these features when you will be testing Firebird 3. I will not be enumerating them, just take a look at the slide. Just maybe a few words about the extensions to outer statements. Outer table, outer column statement, and outer domain statement now allow to change natively the null flag. Also, outer database now allows to change the default database char set. What is the point behind these two features? Now, we, the developer, think that no direct system table updates are needed anymore. So now all the changes that are required for your applications and your development are now covered with native SQL statements. So it's really possible that Firebird 3 will not allow direct system table updates. Well, this is important. So if any of you know about some other feature some other DDL change that's still impossible to do with native SQL, and it still requires system table modifications, please report in the track to the tracker and to the Firebird development list so that we could address your needs as well. So far, we think it's done, but maybe we could miss some modifications that's still required. Actually, it's necessary for us to close all the possibilities for misuse on system tables and thus causing any database corruptions. So, of course, this is mostly related to the tool developers, but maybe you could just review your development scripts that modify metadata, and perhaps there still could be some direct system table modifications that you think still necessary, and they are not addressed in Firebird 3 features, so please report us back about them. Because if you will notice that after the final release, your scripts will be in big problem. And there will be a dedicated session about the security tomorrow, and Alex will be presenting all the details about that. Just a small overview of what has been originally planned for Firebird 3. Some of these points, some of these features are already implemented or in the way, in the development right now. For example, the past 3 ones, we have patches by Redsoft that implement these features, but these patches should be reviewed and modified to be applied in the Firebird 3 code base because they're quite old and they have some problems with the past reviews of these features, but we still hope them to be integrated in Firebird 3. It's not done yet, but it's in the pipeline. As for the encryption abilities, Alex will be speaking about that separately, and more details will come tomorrow in this regard. Now, what was the primary goal on Firebird 3? The primary goal was to implement a super server. By super server, I actually mean an architecture, a multi-threaded architecture with a shared page cache that is really can scale in multi-core and multi-CPU boxes. Yes, this work is mostly done, and the results are being tested now. A few adjustments and a few related features are still in the work, and they will also require some testing, but mostly we can say that this goal is almost achieved, and as soon as the remaining pieces are done, and as soon as the architecture in ODS are known to be stable, then Firebird 3 Alpha will be released. We are really quite close to that, surely not this year, but most probably the first quarter of the next year, Alpha will be ready. How the SharedCache architecture of Firebird 3 looks like? Actually, this picture is mostly the same as for Super Server in older Firebird versions. When this is shown, a single server process is shown. This process has a page cache that's shared among user connections. Every user connection is handled by some thread dedicated from the pool. Besides user connections, there are 2 system connections. They are shown here as cache writer and cache reader. Cache writer just cleans out the page cache by removing the dirty pages to disk, by writing them to disk. For example, if you have small cache and perform batch modifications, the server tries to read the databases into the cache, modify them in memory, but finally all the page cache, the entire page cache becomes full with dirty pages, and you need to read some new pages into the cache. So all pages must be written to disk. This is performed by a background thread known as a cache writer. And the cache reader is something new in Firebird 3. Actually, there may be a few cache reader not processes, threads, and attachments. It's a prefetch of the database pages. So when some table scan requires, for example, a known set of known data page numbers to be read, so we have this information in advance, we notify the background thread, the cache reader, that we will need these pages a bit later. And while we are still processing a single database, reading records from there, unpacking them in memory, and returning them to the user, the background thread reads the next data pages from disk to the page cache. Actually, there are many times when these information could be known to the optimizer, so that not only full table scans can utilize the prefetch. Index range scans, for example, if the range is wide enough, and if the selectivity shows that actually very many data pages will be read through the index. It's also useful, and some nested subqueries also can benefit from the prefetch. The page cache is directly connected with the database and with the log manager. In SuperServer, actually, the log manager is not used for handling pages. All the logs are done inside the single address space. These logs are quite optimized for the inter-process usage. We call them latches. But if we start to speak about classic, super classic, and so on, when multiple processes could access the database, and every such a process could have its own page cache, the log manager appears to and starts to work in order to communicate with other processes, with other page caches, and guarantee the synchronization between them, between processes and between different connections that are handled by different page caches. How it's going to work from user perspective? There are two options in Firebird.conf that configure all of these working modes. The first option is named SharedCache, and it provides an ability for multiple connections inside a single process to share the database page cache. So it just, if this option is turned on, then the second, third, and other connections would attach to the same cache. If this option is turned off, then they will be provided with their own private caches. And SharedDatabase, it allows to share a database file by different page caches. Most often it's about classic, when the database file is shared by different processes, server processes. But actually, super classic works the same way. The process is still the same, but different connections inside this process have separate page caches, and they are accessing the database file separately. So it should be opened in the shared mode. And how these two options could be combined, and what do they provide? First of all, let's see. SharedCache is turned off, and SharedDatabase is also turned off. You connect to the database. Of course, the database file is available to you. Sharing is disabled, but you are the only one user of that database file, so you are allowed to attach. And actually, with one connection, it doesn't make any difference between whether it's shared cache or separate cache, because you are the only one accessing it. So your connection is allowed, but the second connection will fail, because the shared cache is not allowed, so a separate cache will be created, but shared database access is not allowed. So the second instance of the page cache cannot connect to the database. So error will be thrown, and this mostly looks like single attachment only options, in some way similar to the database shutdown single mode. But single mode allows only sysdba and DB owners to connect. This mode allows whatever users to connect. Actually, I don't really think it could be very of any use in practice, but perhaps some of you could find it useful. I don't know. Actually, it's just an implementation option that becomes available, but it was not really the intended usage. But it works, and it works okay with these limitations. If we turn on the shared page cache, then the second connection, the third connection, they are attached to the same page cache, and actually we have a super server. Nothing changed if we compare this working mode with all the Firebird versions in the super server architecture, except their concurrency performance and scalability. So all you need is just to set up shared cache, to allow the shared cache, and disable the shared database. It will ensure that only one process can work with the database, and it allows to optimize the performance a bit. I will speak about that in the next slide. If you exchange the options and enable the shared database but disable the shared cache, it's actually classic and super classic. What is the difference between classic and super classic here? The options are the same. Actually, it's the same as in Firebird 2.5. If you specify the M switch in the command line of the service, the super classic starts. If you don't specify the M switch, then regular classic is started. So it's actually an option to the network listener, whether it starts a new process for the new connection or whether it starts a new thread for the new connection. The architecture the same, the options in the configuration file are the same, just a different switch in the network listener. And a kind of weird mode when both options are enabled. I have marked it as special. Why? What it means? You may have one server processor handling 10 attachments and another server process handling another 10 attachments and so on. So it allows you to flexibly balance between threads and processes. For example, if you are sure that some operating system, for example, better handles load balancing for processes than for threads inside the single process, but you don't want to use classic. You want to have a few attachments in one process and a few attachments by another process. By this would allow to decrease the kernel resources of the operating system. It becomes possible, but actually it involves a lot of inter-process communication and a lot of synchronization. Every cache will be synchronized internally and externally through the log manager. Also, all the modifications of pages will have to be transferred between processes through the disk. So, in fact, this working mode is unlikely to be used in production. At least we think so in more production systems, because it's just overcomplicated and its costs are really big to noticeably affect the performance. One possible use of this working mode could be if one day Firebird project would decide to offer a feature to run UDFs in the separate address space in some dummy process to isolate it from the other processes. But this UDF starting with Firebird 3 can easily access the database, run queries in the same transaction context, for example, as the main query. So this second process, this is actually running the UDF code and allowing it to connect back to the database. They will have to access the database, and if a direct access, the embedded access, will be allowed in this case, so that the UDF will not have to go through the network, but will call the procedures and running SQL statements natively, embeddedly. So it means that even if you have a super server with a shared page cache, this second process still has to access the database. So it still has to have its own page cache and so on. Maybe it is the only practical example when this working mode could become really useful. But so far, we don't offer this feature, and it's not scheduled for Firebird 3. I mean, running UDFs in the isolated process. So it's really possible that this mode could be disabled in Firebird 3. Just because of its costs and its complexity. Right now, it has some problems in the current Firebird code base, but those problems are known. It will be addressed. But even if everything is fixed, perhaps this mode just won't be useful to anyone. And if you, our users, would report that it's really the case, that you don't need it in production, it would be better to disable it in Firebird than allowing any misuse, and a lot of complaints in support lists that it works terribly slow, it's locking itself, and so on. The default option is, of course, the super server mode. SharedCache is enabled and SharedDatabase is disabled. How it works from the synchronization point of view. The page cache, the shared page cache, is internally synchronized using low-level locks. They are known as Latches. It's mostly a kind of read-write lock, but with a few additional features. And any cross-process, mostly cross-cache synchronization is provided by the lock manager. So actually both locks work the same way, but some of them are optimized and implemented for single process performance and single process optimization, but what we refer to as locks is provided by the lock manager. It's handled by a separate lock table and is intended to be used in classic and super classic architectures. When you first connect to the database, this is the first connection, the shared database option is being checked by the engine. If shared database access is disabled, then the database file is opened in the exclusive mode at the file system level. So, shared database disabled means that any other connection from other process, from the other cache, will be trying to access the file, try to open the file, and report the error. Then the cache, the page cache, starts up. All the latch subsystem is set up, it's initialized, but the lock manager is not involved in this point. The locks are allocated, but they are not acquired. The lock manager is not in the game yet, because we are only single connection. We don't need any lock manager synchronization. And actually, you start to work in the single connection mode with only latches. Actually, this so far is how Firebird 2 2.1, 2.5 work. Nothing is really different. Besides that, older Firebird versions don't have the shared database option. Then, imagine a second connection coming. This time, if shared database could be either on or off, but the shared cache is enabled, and the second attachment is inside the same address space, the same process, then it just attaches to the existing page cache. Latches are still in game. We have two connections accessing the same cache internally inside the single address space, and they are still synchronized with latches. Locks are still not involved. As soon as some separate cache instance is activated, mostly it means second classic connection is made from the different process. The initial connection, is notified about that he is not an exclusive connection anymore. Some other connection is requesting the shared database access. And if shared database is allowed, then first connection activates its locks. So it activates the lock manager. It has all the locks already allocated, but they were disabled. They were not acquired. The lock manager didn't grant any locks. At this point, all the locks that should have been taken but were not taken due to the optimization are being acquired. At this point, both latches and locks are involved in the synchronization. So the first page cache is handling synchronization with both latches and locks, and the same way works the separate page cache, the separate classic process. So now we come to the two-level synchronization. Of course, it's more expensive, but that was always the case. If you run classic, IPC is your bottleneck. So inter-process communication, lock table, shared lock table, and the lock manager are the things you must care about. So previously, without these options, they actually were precompiled with super server in one way and with classic server in another way. Now, every decision is made in runtime accordingly to the chosen options, shared database and shared cache. Now, about what has been achieved with shared page cache and how does it scale. Of course, it's too early to do any benchmarks, especially comparative benchmarks, because Firebird 3 is not even in the alpha stage yet, but it's more or less stable in the super server mode. At least all our concurrency tests and high-load tests are running successfully. The server don't crash, and no any unexpected lockups happen. So some initial observations could be made with Firebird 3. What was the goal? The goal was to allow some better scalability than the regular super server, the older super server, by providing low-level synchronization in the page cache. There are different blocks inside the page cache, but mostly the contention is about page-level locks. So every page has a dedicated latch and a dedicated lock in the lock table. Now, if you run super server in multi-core hardware, multi-CPU hardware, with the lower level synchronization, better scalability can be achieved. How much better? This is the question. So far, our efforts were dedicated to stability. So we don't have any, let's say it, advertising bullshit ready for you that Firebird 3 is really great, that it beats everybody else, it's going to occupy the whole earth. No. We are concentrated on stability and concurrency both ways, but what can be seen right now by comparing Firebird 3 with Firebird 2.5? I've just done a small concurrency test. It's not about to prove any major improvements and so on, just to demonstrate what we have now. It's not about what should be expected in the final release, but what we have now. The red line is Firebird 3. The blue line is Firebird 2.5. The test was quite common. It's a TPCC benchmark, but it was running on a regular workstation with quad cores. So it's not some real server. But 3 points could be observed from this picture. First of all, the initial performance with only single core, Firebird 3 is a little bit slower than Firebird 2.5. When no scalability is allowed by the setup, I was just setting as a CPU affinity to a single core. Firebird 3 is a little bit slower. I will explain that about that a bit later. Then, when we activate multi-core abilities, when we turn on the second CPU, actually the performance here is shown in transactions per minute. Well, the raise is about 60 or 70% as compared with a single core, and it becomes nearly 50% better than Firebird 2.5. So on 2 cores, we actually have about 60 or 70% of improvements. This is just about the scalability on single core and dual core machines. So some kind of progress is easily visible. So if Firebird 2.5 doesn't benefit at all from multi-core, Firebird 3, the current snapshot build, shows quite noticeable improvement for double core system. But the third observation is that the performance doesn't really raise much when adding third and fourth cores. Why? Well, actually, as I said, it was just a small test on the development workstation. So of course we would be interested to have other testing results on other hardware. But it was first of all, it was a Intel Core 2 CPU with quad cores. As you know, actually this CPU has 2 blocks. Every of them has 2 cores inside and its own level 2 cache. And they are connected with another 2 cores by separate bus. So, if you run your queries on the same chip, the performance is much better than if you run them on the different halves of the processor. This is why the third CPU doesn't really improve the situation, because the cross-communication between 2 halves of the processor is actually quite expensive, and it doesn't allow any noticeable growth of performance. Also, if we add fourth CPU, fourth core, one would expect that third and fourth cores are still on the same chip with the same level 2 cache, so it should provide more performance. So the third part of the line should raise higher. Yes, I agree that would be expected, but don't forget that we still have the operating system running on the same box, and the testing applications also generate some CPU load. But we don't have any more cores for them to utilize. Up to the 3 cores, Firebird was running separately from the operating system and the testing application. With all the cores being utilized, they have to share the same resources. So I believe it could be one of the explanations that the race is not that high as some of you could expect. But as said, this is just one side of the coin. As you could notice, I have provided CPU graphs for both Firebird 2.5 and Firebird 3. The difference is quite noticeable. The CPU usage is very noticeable. But this test is completely CPU bound. You can see that all the cores are close to its upper limit. If this test becomes disk bound, situation could change significantly, and Firebird 3 could actually it would allow much better scalability in this case. Because especially, it could be interesting that in this case, I would expect Firebird 3 to, even in the single CPU case, to work better, to perform better than Firebird 2.5. Because every disk access allows concurrency, but Firebird 3 is much lower level synchronized, so it allows better concurrency. So this test is quite artificial. It doesn't show real situation in production. It just shows how much better we can scale in the CPU-bound tests and CPU-bound database access patterns. Of course, we would be much interested to see other tests. Both, it's not about a comparison with Oracle or with all the Firebird versions. It's just about how the pattern, the load pattern, would depend on force writes turned on or off. Here we have 4 cores. What would be with 16 cores? For example, I would expect the growth much higher, and without this second part that doesn't show any improvement. And of course, different loads, different kind of load for different databases and so on. How big part of the database can be cached by the file system and so on. So it's not a performance benchmark, it's just one of the usage patterns and how it could be explained. But one more word about this. Mostly about single CPU, not maybe about this test, because here we have 10 concurrent terminals running even on the single CPU. But imagine the simplest possible test case. You are the only one attachment, there is no concurrency, and you run some very simple statement that cannot be optimized any more than it's done currently. For example, you select one record through the primary key. What could be the performance difference in this case? It's really possible that Firebird 3 could be a bit worse regarding performance in this case. Why? The explanation is trivial. Any synchronization complexity added has its costs. And some of these costs are, unfortunately, impossible to remove. Single-threaded performance always conflict with the concurrency. You see that, for example, Firebird doesn't use page-level locks if it's possible to avoid them. It allows a lot of improvement. But for Latches, I don't expect any more optimized code that we have now. It's actually not about Firebird only. If you would look at any other database engines, the situation is pretty much the same. I was searching for some public reports, and this is for MySQL situation. If you follow the MySQL development, you could notice that any recent MySQL version, I mean in the DB storage engine, noticeably improves multi-core performance. They had a lot of problems with that in the past. Now they scale better and better. But here you see the cost. The newer MySQL version you test, in the single thread, simple cases, the slower it runs. Believe me, the same test could be done for Oracle, and the result will be the same. Just maybe different numbers, different percentages. But it doesn't mean that we cannot do better than MySQL. Of course, some improvements are possible, but it's not about optimizing the locking internals or the latching code to death. Not. It's about optimizing other data access paths that would allow better performance in the real-world queries. For example, if you have, well, for Firebird 3, personally, in some queries, I have noticed performance degradation maybe 5 or 10% if compared with Firebird 2.5 in the simplest single connection test. But you know that any good change in the optimizer can provide 10 times better performance, 100 times better performance, and so on. Table prefetch could allow better performance for natural table scans and selecting count from big tables and so on. Actually, there are a lot of ways, alternative ways to improve the performance. And we'll be addressing them, researching them, and addressing them to compensate the negative impact of the more complex synchronization in Firebird 3. So actually, you shouldn't be afraid of a very slow engine closer to the final release. No. There will be other improvements that would compensate, or maybe almost compensate, even simple cases like the one I was mentioning. Of course, in real-world queries with complex queries, we expect better performance, not only because of the locking, but also because of the changes in the optimizer, in the internal algorithms, and so on. So just pay attention that nothing can be achieved for free without any cost, and but don't be afraid. So some other optimizations are also possible, and the final result is likely to be positive. What Firebird 3 can offer besides the SharedCache cache? It introduces new ODS version, ODS 12. It's not compatible with prior ODS versions, and Firebird 3 is the only Firebird engine that can work with ODS 12. There are a few changes in the physical layout of the pages on disk. Of course, there are other changes in system tables and the monitoring tables and so on, but they are not major. You may notice new system tables, new fields in the existing system tables, but it's still just to support new features. But there are a few major changes in the on-disk structure that are related to the performance. First of all, every data page and corresponding pointer page has two new flags. One of the flags is so-called secondary page flag. It allows to distinguish between primary and secondary data pages. What is a primary page, a primary data page? It doesn't, the page that contains at least one record in its original version, that head version. You know that record versions are stacked, and the DB key points to the first one, to the head record version. And all the other record versions are accessed by the pointers from the first one, from the head version. So, primary page, it contains at least one head version of some record. Secondary page is known to contain only back versions, record fragments, and perhaps small blobs. So it's not all of its parts are accessible only through the previous record version of previous record fragment, previous data page. What does it mean? It does mean that the natural page scan, natural table scan, which must read all the data pages, could notify this flag and just skip secondary pages because they don't have any head versions inside. Of course, if you don't have any modifications and maybe your table are quite small and the fragmentation is small, this improvement won't provide you with really benefit and from the performance point of view. But if you have a lot of small blobs in your tables and if the records are quite long to be really fragmented, and if you have a lot of back versions in some table, this improvement allows to read the whole table faster. The second flag for the data page is the so-called swept flag. It also available in both data page and the corresponding pointer page, and it means that all the records on this data page don't have any back versions, and they are guaranteed to be created by the already committed transactions. What does it mean? It does mean that the swept pages doesn't have any garbage to be collected. So the sweeper may skip these pages. It could noticeably improve the performance of the sweep. And a very different feature, but somewhat related, we have introduced a new page type. It's known as a SCN inventory page. SCN is a system change number. Every data page has its own system change number. Every time a database backup, I mean physical backup using NBAC, is started, new system change number is generated. And pages modified after that point would have different system change number. How NBackup works now? For the level 0 backup, a full copy of the database or just reads the whole database, all the pages sequentially, and makes a file system copy. For an incremental backup, level 1, 2, or more, it still has to read all the data pages, but check whether its system change number has changed since the last backup time. So whether it should be written into the backup file or not. The system change number is stored in the every database page. So it allows to create much smaller incremental backups, but the database still has to be read entirely as a whole, all the pages. With Firebird 3 and its ODS 12, this system change number inventory page stores some kind of relationship between system change number and page number. So the NBackup level N, so incremental backup, may read the inventory pages, compose a list of data pages that were modified by this system change number, and write into the backup only necessary pages, but also read only necessary pages from the database file. In practice, it means that if previously you set up NBackup to have, for example, once per 5 minutes level 3 backup, you would still have the whole database read every 5 minutes. Now you will have only 20 or maybe 100 pages read every 5 minutes. The improvement is really huge, and in fact, it may even allow you to have, for example, every minute backups and so on, because it just becomes physically possible. Previously, it was impossible if you have a large database. And of course, if you run a level 0 backup, nothing is changed because the database file must be read entirely. Nothing can be done with that. But incremental backups now will be much faster than before. Now, a few words about the optimizer. This is my favorite topic because it's, well, we have a lot of improvements and of course they are important, but it's always more funny to tell about the things that you are doing yourself. So this is kind of my favorite topic. There will be a few improvements in the optimizer area. Some of them may be more important than others, but anyway, I will explain what is already done and what is expected to be done a bit later. First of all, if you followed the development list or attending the prior conferences, this feature was already presented. It's an ability to get detailed plan information. It's optional, so because first of all, we don't want to break any existing parsers of the plans and so on, and because the plan itself is sometimes also useful, so it's available the same way as before, but our API has been extended with a new option to retrieve a detailed plan. It's still the text, but much more detailed than before. It contains all the operations, because the current plan report only major operations, but doesn't show, for example, any Boolean filters, doesn't show the aggregation except the sorting. It doesn't show any first or skip statements in the plan and so on. The new detailed plan output includes all kinds of operations the server is processing. They are reported in the hierarchical view, so you can see what is executed first and how records are passed to the upper levels and processed again, and so on. Some additional details are available. For example, for a join, you will have an information whether it's inner or left outer join, and some more details will be available in the future. Right now, this change is already available in snapshot builds, but only in the simple form, without much details. I will show that with example a bit later. Oh, okay, let's see it right now. For example, here is a simple join with one condition that cannot be satisfied with an index. And here is the original plan. And here how one can look in the detailed way. So you can see that we have a join that is implemented with a nested loop algorithm. The join is inner, that its first stream, the leading stream, performing a full table scan of the orders table. Then a Boolean filter is applied, so we have this condition evaluated after scanning the table for each row. And the second stream, the dependent stream, is a table access by ID. ID means DB key. IDs are taken from the bitmap, and bitmap is populated with the index scan. This is just the simplest form that's available right now. It will be extended closer to the beta release to include other information. What other information? For example, here there could be additional information of what kind of index scan is that. Is it a unique scan? Is it a range scan? And so on. If it's a range scan, what are the boundaries? Do we have only the lower boundary or only the upper boundary or both? And so on. For a full scan, we could provide an information whether it's the scan will be reading everything by itself or will be coordinating the reading with the prefetch. Filter could here the exact condition be mentioned here so that we know that here we have this boolean, this predicate evaluated, and here we have another boolean evaluated. And most important, cardinality and cost estimations that are used by the optimizer will be printed in the detailed plan as well. Every node in the output will have additional row of information that will show you how many records are expected from this part of the stream, from this particular stream. So how many records will be read by a full table scan, how many records will be remaining after filtering with the predicate, how many records will produce the loop join because there can be multiplication for both streams. So, and not only cardinality estimations, number of rows, but also the costs with the optimizer. So it could be quite visible why the optimizer has preferred this particular plan and why is it known to be cheaper than some other plan. With the current snapshot builds, there is no such information, but it will be available in future builds. And it's possible that one more information could be added. You know that we have now just prepared the query and the plan was generated. There could be cost and record estimations for this plan, but they are still estimations. After running the query, you could know exact row counts for every node of the plan. Because, unless of course you have already destroyed the statement and its plan. But if you executed it and right after that with a valid statement handle would ask for a detailed plan, it could show you the actual information about how many rows have been processed and perhaps even some runtime statistics, disk reads and so on, CPU usage. But it's just so far it's a raw idea that can be implemented, but so far it's delayed closer to beta and release candidates stage. Another new feature that Firebird 3 will offer is an ability to materialize subqueries. It means that some stream will be read and cached inside some buffer, temporary buffer. It doesn't mean that there will be a delay while reading from this record buffer. If you access the cached stream row by row sequentially, it will be caching, it will be cached also sequentially. So if you fetch one row from the buffer stream, it fetches itself one more row from the underlying stream, stores it inside, but sends it back to the user. So unless you have read the entire buffer, the entire stream, the buffer will not be completely cached. But if you fetch the first row and then you fetch the last row, between these two fetches, the whole buffer will be collected. Why? One more point. The storage behind this record buffer is located in the temporary space, and handled by the temporary space manager. And the performance of this record buffer highly depends on the temp space limit option of Firebird.com, because this option defines how much physical memory will be used for the temporary space, in this case for the record buffer, before it will be overflown to the disk, to the temporary files on disk. So, of course, if you have some plan generated by the optimizer with the use of the record buffers, materialized subqueries, you must ensure that you have the big enough setting for the temp space. Otherwise, you might have quite big disk reads and writes because of the swapping the buffer to the disk. Of course, the optimizer will be doing its best to decide whether to use the buffer or not, but still some setting, some tuning could be required with the Firebird.com. What queries could benefit from this feature? Obviously, invariant subqueries. Or if you exist clause or in clause or not in clause have a subquery that is not linked to the outer query, so now it has to be executed for every outer row. So a lot of time the same subquery is evaluated and the same rows are from disk. With the record buffer, of course, they will be cached in memory and accessed much faster. Another option that could use the record buffers is the hash joins implementation, and I will speak about that right now. Hash join implementation is the third one available in Firebird. So far we have a nested loop join and the sort mesh join. Now hash joins offer the third ability to perform to join two or more streams. How does it work? We just decide which stream is bigger and which one is smaller. Read the smaller stream into the record buffer. Create a hash table for every join key based on this inner stream. And only after that we start reading rows from the bigger stream. It becomes a leading stream. Every row fetched from the leading stream has the appropriate hash value generated based on the join keys. And there is hash lookup in the hash table to find the list of possible matches, collisions for this join key and this hash value. What is the benefit? If join cannot be done using an index, it means that nested loop join will be reading the second stream, the nested stream, again and again and again and so on. So it really becomes, well, just make a very easy sample with two tables, joining them with a natural scan, so it's in both sides, and you will understand easily what I'm talking about. It's never going to end. Hash joins allow to cache the second stream and access it from memory instead of accessing it from disk. Also, if, for example, your nested stream is not a table access, but it's a union of 5 tables with aggregating outside, you will easily understand that executing that again and again, even if it produces just a few rows as a result, is going to be terribly expensive. Hash joins allowing to avoid such bad evaluations and read and execute some nested stream, some nested subquery only one time, and then refer to the cached results. You might ask, how does it better than the merge join? Merge joins work in the same way. It also allows to skip multiple executions of the nested stream. But the merge join requires sorting of both streams. If the streams are small, finally the result is small, but the sorting file could still be big enough. For example, if you have a group by that reduce 1 million rows to just 10 rows, you know, the sorting costs a lot, but the result is very small. Hash joins are known to perform better than merge joins in many conditions. But merge joins, of course, would be a better choice when one of the streams is already ordered by the join condition, by the join key. So you don't have to sort it the second time. In this case, the optimizer will be using the merge join. Otherwise, a hash join. If an index can be used and the cost of multiple index scans from the nested stream, the total cost, aggregated cost, will be quite low, then the optimizer will still be using loop joins. So actually, maybe for a lot of retrievals of many tables joined by the primary key, it's not going to provide any improvement. But for more complex queries, for joining subqueries, derived tables, and so on, the difference would be much more visible. And other something related and not about nested loop joins, I had already explained. The full outer join has been completely redesigned. Previously, it was never able to use any indices. Now, indices can be used for both parts of the full outer join. Both hash and the merge join types will be supported for outer joins. It's not possible currently. Some conditional retrieving is already implemented and available in the snapshot builds. For example, the common pattern of passing some variable and selecting either some particular value or selecting the whole table based on this variable. This condition previously could never use an index because before evaluation of the parameter, you don't know whether you need to read the whole table or an index can be used to locate just one record. So the optimizer, of course, was choosing the common but less optimal way to read in the whole table. Now, an index could be used for these conditions. And some other improvements in an advanced evaluation of constant predicates that are known to be true or false before running the whole query. And there is ongoing research regarding hash-based aggregates. Let's see. Oh. Just a couple of examples. Here you see a join with explicitly disabled index lookups. And here is the plan. You may see a hash join, and you may see a record buffer for the inner stream. So everything is reported in the detailed plan, and you can analyze what is going inside, what's going on inside. Here is an example of the full join implementation with using indices. Here is an example of a new conditional evaluation. The optimizer actually prepares both ways of accessing the table, with a full table scan and with the index lookup, but it switches between them at runtime accordingly to the past variable value. Another thing related to the optimizer is an improved statistics that the optimizer can use to generate better plans. Currently, we have only index selectivity. It's stored inside the database. And we have an estimation of the record count. I have been talking about that a bit earlier. Firebird 3 will introduce new statistical tables that will store all the information required for the optimizer, including number of data pages, fill ratio, number of index pages, the depth of the index tree, the compression ratio, the clustering factor for the index, and so on. And all these values will be stored in new system tables and accessed by the optimizer. These statistics will include histograms for the indices and not index columns as well. So we really hope that the optimizer will be able to use better decisions than previously with this information. Of course, you are still required to update the statistics regularly, but some automatical recalculation of statistics could be possible by the engine itself. For example, if it notices a very big difference between cost estimation of the query and the actual cost after executing the query, it could understand that the statistics is very outdated and requires recalculation, and the background thread could be run to collect the statistics to be updated. Or, for example, if number of records estimated by the data pages is known to be big, but the statistics has a number of records too small, so the difference between the stored value and the estimation is quite big. Again, the statistics could be forced to be recalculated and restored. And one of the final parts of my presentation is about the monitoring abilities. You know, every Firebird version has some new features in this regard. There will be a few different extensions of the monitoring tables, of the existing monitoring tables. For example, we have considered providing more information about the disk input-output. Right now we have only fetches, marks, reads and writes. But, for example, it could be interesting to know whether the reads have been achieved synchronously or asynchronously by the prefetch, whether the page writes are performed by the transaction commit, or because the dirty pages are overfilling the cache and have to be written to the disk, or perhaps the data page has been written because of the asynchronous request in Classic. That's another process need access to this page, but it's dirty, it has to be written to disk, for example. Also, as we have a new temporary space manager that works in with both memory and temporary files, so it's something like the page cache with in-memory access with fetches and on-disk access with read. Perhaps it would be a good idea to include statistical information about the temporary space, fetches and reads and writes, something like that. There was an idea to have statistics for executing statements, how many statements were run, for example, for this connection or since the database start. And perhaps it could be divided into compiles and runs, so that you could estimate how good is your application regarding using the prepared statements. So how many parsers and compiles you can avoid by using the prepared statements in your application. So the statement cache efficiency could be monitored, and so on. And one more improvement that is currently in the work. It's not yet available in the snapshot build, it's being tested, but you have the chance to see it in this conference. It's timing statistics. So it would contain a few values. What time is spent for different operations. It would include the following columns. First of all, total elapsed time. It means how much time has been spent inside the engine. So between the API call start and finish. It doesn't include network round trips and so on, but it does include all the activity performed by the engine to execute your query. It would include disk access, any synchronization waits, the CPU time spent, and the CPU time will be divided into the user mode CPU and kernel mode CPU time. And if you would take the total elapsed time and the CPU time, the difference between them would provide you with the time spent for the waiting. The engine was not doing anything, but it was waiting for anything. The obvious things in this regard is page reads from the disk, waits on locks and latches and other synchronization primitives, on events and so on. So actually, with this information, you will have the abilities to a kind of profile your statements, not really maybe statements, but your activity at runtime, because these timing statistics would be available the similar way as input-output statistics we have now and record statistics. It would be bound to database level, attachment level, transaction level, statement level, and procedure call level. So at every level you would have the timing statistics. Let's see how it could look like. Here we have just some query. Let's wait until we finish. It shouldn't be a very long time. It runs a bit slower than expected. I tried it before the conference and it was faster. Maybe now the recording application also affects the performance. On my slide, I was showing just the basic time encounters that could be used, and the example I will be showing you now also utilizes only a few basic counters of the waiting time, but actually more detailed can be provided. For example, here we have a result. The transaction is still active, so I don't care whether IB expert has closed the statement handle or not. I'm selecting from the time stats, joining in with transactions, and selecting by the current transaction. The transaction is still active, and it was started explicitly right before this query, so the transaction statistics shows the timing for this particular statement. And we see that totally the value is in microseconds, so a minute and a half has been spent by the engine. The reading time from disk was almost 8 seconds, and the rest of the time was being spent in the CPU module, but both the user mode and the operating system kernel modes. So, of course, the wait EO timer could be splitted to show you separately how much time is spent for reading pages, how much time was spent for writing pages, and so on. For other weight modes, weight kinds, there can be also more detailed information available. It's just a raw example. It's just a sketch to show you the idea. It's not ready for committing into the Firebird repository. You can see we have a single connection. So both latch wait and lock wait time is 0. The lock manager is not involved, and we don't have any concurrency, any simultaneous access to data pages. So latching was really not involved. There were no contention on latches. There were no waits on table on page locks and page latches. So if we just see, we have a transaction committed. There are no transaction or statements running anymore, but the statistics have been accumulated at the attachment level and the database level. So every time you monitor your running system, you see which attachment is using more time and what actually this time. Where is it spent? In the CPU, for the input-output, for the waiting, the lock manager, for example, and so on. Here, let's see. Just to compare the single connection mode with multiple connection mode, I'm running the TPCC concurrency tests with 10 terminals, and now connecting to the database and selecting the attachment level statistics, subgroup equal to 1, only attachments. And here I see 12 attachments are active. One of them is mine. Another one could be system attachment, cache writer, garbage collector, and so on. And 10 user attachments are running. They have spent similarly amount of time, and most of that time is spent in the CPU, but actually the disk input output is also quite noticeable, and they have competing for the page latches. The contention is quite high. So actually, they wait at the same, almost at the same level as they were. So here we see that concurrency does have its host, and the threads are waiting for each other for accessing the same set of pages. And we are on super server. There are no locks involved. Zeros are there. With classic station, it will be quite different. You will have zeros for latches, or maybe almost zeros for latches, and you will see wait times for the lock manager. This was just as an example of how it could look like in Firebird 3. And the final thing I was going to speak here in this session, there are plans to extend some length limits, especially in the API. Mostly it's a length limit of SQL statements. Now it's quite low. Well, it could be 64 kilobytes. It's quite big enough for single queries, but complex execute blocks could not fit this limit. And some, for example, batch operations that are available in the standard, if we would implement them, I mean, for example, multi-row insert statements, that it doesn't make sense to offer the features with this limitation because they cannot be used. So we actually Firebird 3 will offer 2 APIs. One is currently internal, and it already has these limits extended. Not many of them, but some of them. The public API is still the same and it cannot be changed. But we are considering providing alternative API entry points in the old style API that would allow you to use longer SQL statements, longer messages, input-output messages, I mean parameters passed procedures, and for example, the whole length of the artificial record. If you join a few tables and select all fields of those tables, the total length of that further record still is limited, but we would like to extend those limits. And there are also some other limits, like the limit of intermediate record stored in the record buffer and sorting record and so on. But it does not mean that the stored record size will be increased. And it does not mean that varchar's maximum size will be increased. So far, the limits of 32 kilobytes for varchar and for 64 kilobytes for a stored record in the table would still persist. But other limits of dynamic records and of physical statements and so on are likely to be extended or removed at all. So my time is over. I'm a bit late actually. If you have any questions right now, feel free to ask, or of course you can find me there or maybe in the hotel for the next couple of days. So any private questions are also allowed, no problem.